Right. Well, welcome everyone to today's webinar from Help Systems and also really from IBM. We really are very appreciative of having Steve Will back for really, I think, about the fourth time now to talk about this similar topic that kind of evolves over time. I'm Tom Huntington and I'll be your moderator. Steve's going to be doing most of the talking today, so you won't have to hear me very long. But we're going to be talking about why IBMI is not AS400 and some updates in 2020 related to the platform. Again, I'm Tom Huntington, Executive Vice President of Technical Solutions at Help Systems. I'm also a 5-year power champion, and so got the honor of being part of that program, and really beneficial to me as we get to learn a lot more about the internals of what's happening around the Power Platform, IBMI, AIX, and Linux on Power. And been with Help Systems now a little over 3 decades, that's all. Steve, how about you? What's your background?
Chief architect now. I've been chief architect for 13 years on this platform. I joined IBM here in Rochester, Minnesota in January of 1985. So 35 plus years working at this place. Yep.
Awesome, awesome. And then just some logistics before we get started. The event is being recorded. You will get handouts afterwards, so you'll get an email from Help Systems with a PDF of the presentation today that you certainly can share. But the recording's there. You can look at it at a later point in time. And we do have Q&A today, so if you have any questions, send them over to the question toolbar, and then we'll read them off at the end if we have time to go through them. Otherwise, Steve or I will get back to you. And then final thing that we have is we'll have 2 polling questions too. We hope that you can participate in that. So enough if we want to turn off the camera, Steve. How's that?
All right, sounds good. Okay, so you ready for me to begin? I think there's a polling question pretty quickly, but as Tom said, we've done this presentation now for a few years. I actually built this presentation to deliver at a common conference. Tom saw it and suggested that a wider audience might want to see it. And so they began sponsoring it. It has evolved over time because the architecture evolves over time. Actually, that's kind of the theme of the presentation. And so we're going to get into this presentation pretty quickly, but I would like to have an idea of how long you've had experience with the platform. So Tom has a polling question.
So let's go off to our polling question here. Steve, how much experience do you have with IBMI? And of course, somebody's going to say, well, I started on the AS400 or the System 38. So that fits into that category of more than 30 years. And really happy to have you long-termers with us. 21 to 30 years, 11 to 20 years, 1 to 10 years, less than 1 year experience on the platform. While you're filling it out, I'll remind you that IBM's just had some recent announcements. One back in April, they introduced NVMe storage for the platform. And what that's doing for you is giving you a lower cost of entry into the Power Server platform. So if you haven't checked out NVMe, you should. It's cheaper and it's faster. We've done some benchmarking with our Performance Navigator product at Help Systems and seen some really good responses to that. Then also just this week, we saw the announcements of new scale out servers. So if you're in the class of 914, 922, or 924 technology, IBM refreshed those models. So let's see how we're doing here on responding to this first polling question. I know it will take a little bit for all of you to get through it. We have a very large audience today, so awesome. It looks like we've had over 80% of the people vote already on this, so I'm going to close the poll, Steve, and then I'm going to share the results here, so you should be able to see those. All right, wow, looks like we have a good mix of people, 67,
yeah.
You see that?
I can. It's really good to know that there'll be some folks who've been around from the beginning, but 2/3 of them haven't, and so there's some stuff at the beginning that they may need to hear for the first time. So good.
Awesome. Yeah. So thank you for answering that. We'll have one other poll that gives Steve a little break in the middle. So I'm going to hide this and back to you, Steve, and you should be able to move your slides ahead.
All right, cool. All right, so let's get going. This is a 75-minute session because just 60 minutes has grown to be way too short. So I'm going to talk really fast, but this is one of my favorite things to talk about. So if you can listen fast, I'm going to talk fast, and we're going to learn a lot during the rest of this hour and 10 minutes or so that I have for the content.
And Steve,
Now,
just so people know this is
yep,
live, your video is still on. If you want to turn it off, you can. If you want to leave it on, that's your choice too.
thank you very much. I'll leave it on for now. If
Okay.
I need to move around or something, I will turn it off. Thanks very much.
Okay, awesome.
All right, cool. All right, so the IBM RA architecture is something that I will often throw into a presentation, and I will talk for a couple of minutes about this particular slide. It has the 5 core elements of the IBM I architecture. Usually when I'm putting it in a presentation, it's because I'm educating either some technologists who've not used it before or executives who've not had it in their previous jobs, and they need to know something about it so they understand their environment. And I will spend just a few minutes on it. The problem is that when I do this sort of a chart and I'm at, say, a local user group, I will often get some annoying person, some person who knows a lot, who will say, hey, wait a minute, you just called that thing the IBM I architecture, but really, that's the AS400 architecture. I recognize all those things. Or if they've been around a really long time and come from the System 38, they may say, in fact, I'm pretty sure that's the System 38 architecture you're calling the IBM I architecture. And while there is some layer of truth to that, the architecture that we have on IBM I today is really an evolution from 2 or more architectures, the System 38 and System 36, that converged into the AS400 and has evolved through time. And what this presentation is going to do is talk about that evolution, talk about things that were there from the beginning, things that had to be added and changed over time, until now we're finally, 32 years after the introduction of the AS400, at a place where IBM I, while it does have roots in the original architecture, has an architecture that's significantly more advanced than it was back then. And so we're going to start from the very beginning, which is pre-AS400, and talk about the architecture, and then we're going to evolve it over time. Now, I simply, even in 75 minutes, do not have time to do every piece of the architecture. In particular, I can't give you much in the way of education on parts of the architecture that have gone away. So we'll have to do another one sometime about things like that. But in any case, I think you're going to learn something, whether you've been with the platform for more than 30 years, as a third of you have, or for under 10, or under 20, which it looks like a bunch of you have. So here's that architecture. It has 5 key elements. It's how you manage data on the platform. That's the integrated database and single level store architecture, which is unique to the platform. Then a number of different security and integrity parts of the architecture, which are unique to the platform. In particular, the object-based nature of the platform is unique. And then there's a level of virtualization on this platform, which other competing platforms had to actually invent things like hypervisors to try and give you. There is the integration of the underlying, what people have come to term middleware, things that solutions need to be built on top of, that has been part of this platform since the very beginning. Now, we've obviously had to integrate more and more and different things, but that architecture to integrate those things has been there from the beginning. And then we have this thing called the technology independent machine interface. I'm going to spend quite a bit of time on that. So those are the 5 key elements, the 5 kind of cornerstones of this particular architecture. And we can start up from the very beginning by saying, when most people learn about our architecture, they come from a place where in school they learned general architecture has a very simple architecture compared to the IBM I architecture. In a general architecture that you learn about in school, or something like what a Unix is, for example, there are user programs, application programs, and system programs that all use this very thin layer that people often call the kernel of the operating system. And that kernel is merely virtualizing the hardware processor, the devices, the memory that's underneath it. And that's a valid way to do an operating system. Those things exist, but from the very beginning, our architecture has been different from that. Now, I've taken this from this picture from one of the original publications that came out with the original AS400. So it has the OS400 labeled on it, but it talks about how the operating system is really split in the original machine into 3 layers. There's the thing called OS400, and it's not at the same level as applications. It's underneath every application. And then underneath that, there are 2 more layers, the vertical microcode and horizontal microcode. And between there's this thing called the MI, or the machine interface, or the technology independent machine interface. You see, applications and the upper level of the operating system are compiled to this set of virtual instructions, this machine interface. And these virtual instructions are then implemented down to the hardware by the things that are below that MI layer. So even the operating system is split into these layers, and then software which is compiled gets compiled down to this MI. Now, one thing about this chart, and I won't mention it very many times for the rest of this presentation, I've taken that 5 cornerstone icon chart and put it as in the lower right corner, and I've left white the part of the architecture I'm talking about. So as we go through the rest of this presentation, when I'm talking, I have that little icon down there so you can see which of the 5 things I'm talking about. And often I'm talking about more than one, because we are changing multiple layers of the architecture at the same time in order to accommodate changes in technology. So this makes us different from the IBM, from other operating systems. And so you can tell that what we're talking about there is the technology independent machine interface. Now, one of the things that everybody who's been around this platform for a long time knows is different about this platform is how we manage storage. This storage model is actually goes back to the System 38 days. It's called single level store. What it means, for those of you who haven't heard about it, who are fairly new to the platform, is that we treat everything that we store as if it's stored in memory, even if it's going to be put on a physical storage device like a storage drive. Okay, so everything gets an address, a single level storage address, a pointer to itself, and that pointer doesn't change even if you store it in memory or if you store it out a disk. It doesn't matter. It's got that address, and we view everything that can be accessed by the system as one continuous address set. And as I mentioned, that comes from the System 38, that particular part of the architecture. This has allowed us, since the beginning of this architecture, since the beginning of the System 38, to spread our data across all the attached storage devices in whatever way made sense to the operating system. So we haven't had to have storage administrators in the same sense that you have to have storage administrators on other platforms. On other platforms, somebody has to notice that there's a lot of data being put on one storage device and very little on another storage device. And if we move things around and balance them, then you get better performance. You don't need to do that on our operating system because we take care of that for you. That is one of the many benefits of the single level storage part of the architecture. It makes us different, and it comes, we still have single level storage, it comes from the System 38. Part of that architecture is that if everything is going to have an address in this long address space, then that pointer, that address of the thing, that's a special thing. It has to be treated special. And so we created from the very beginning this thing called tags, where every part of memory which contains a part of an address gets this little extra bit that says this is not just data being stored here, this is a part of an address. And so it has to treat those pieces of storage that are holding pointers, that are holding addresses differently. You can have heard people talk about the 65th bit or something like that. What it really is talking about the fact that these pieces of memory hold pointers and therefore need to be treated differently. And they're treated differently, not only in the operating system, but all the way down to the hardware. And that has carried forward as we moved into the power processors and the power processors that we have today. So System 38, single level store, was there. And then we moved into AS400. We combined the architecture of the System 38 and the System 36, made the AS400. And now we had single level store. And was it the same already? No. One of the themes of this presentation is that we had to evolve. We had to change things. So anybody who thinks that it's the same as it was way back at the beginning is only conceptually right. Architecturally, it actually changed significantly, because from System 38 to IBM I, or from System 38 to the first AS400, single level store changed. People started seeing the value, even if the operating system was going to treat everything from 0 to all ones as one single address space. We might want to group those things differently and manage them at least at a gross level of groups of storage differently. And so the AS400 architecture created auxiliary storage pools where you could group a bunch of storage that you wanted to treat differently from other groups of storage. Now, still everything had a single level store address, but it could be managed differently, and that was different. And we'll get to independent ASPs eventually. Okay, so even from the first System 38 to the AS400, we already changed the architecture around one of the key defining elements of the architecture, which was single level store. Another thing that changed from the System 38 to the AS400 was how we do our integrated database. The integrated database is also a part of this operating system, which is very different, unique in the industry. It is the database is the operating system. And what you see today is still the core of what the database is today. There's an SQL interface, then there's these older interfaces. But in fact, we had to incorporate the way that database was accessed from both of our prior systems, System 38 and System 36. And those things had to be incorporated in AS400 and still exist in IBM I today, though in modified form and not used very frequently. Object orientation is another part of the architecture, still a part of the architecture today. It's somewhat different in how it's being used by things like PASE, which I'll get into eventually, but the object orientation makes us different from other platforms. On other platforms, a file is often identified as to what it can do based on the 3-letter extension. This is a text file, this is an image file, this is an executable file. You know that by looking at its extension. No such thing on our platform. There is an object type, and those objects can only be operated on by the operators that are possible for those objects. So if you have an executable, you can't edit it, which is not the case on other platforms. If you have an edit kind of file, you can't run it. That doesn't work on this platform. So that is a key part of this architecture, which makes us different. And yes, it's still part of what we do in IBM I today. It allows files and programs and other object types to be treated differently because we know that they are encapsulated and they can only have certain things done to them. So we had this brand new architecture. I did not go into all the pieces of the architecture, but we had this perfect architecture. But over time, stuff happens that makes us change the architecture. And while V1R1 of AS400 was a beautifully architected machine, something happened. And what you'll find through the rest of this presentation is that something happens either in the industry or in the market that makes us need to adapt our operating system. So what happened? Well, single level store, remember that wonderful thing, even though it had multiple ASPs, there was stuff happening in the industry that was going to make us change how we managed that stuff. You see, when we first came out as a platform, we had a couple of languages that everything were written in, the original RPG and very old COBOL. And those languages were so nice at the beginning because they didn't have something that future languages did, like very soon after we released AS400, the C programming language was very, very popular, and we decided in V1R2 we had to support C. Well, C had pointers. RPG and COBOL, while they do today, didn't have pointers at that point, and so we didn't have to have an architecture that dealt with pointers the way you could in C. You see, if you've never programmed in C, one of the things that you would immediately become aware of is that C only uses pointers. It talks about its variables not as the variables themselves, but as addresses to the variables. And you have to be very careful about how you're treating those things. And so you have to be able to deal with pointers. Why was that a problem? Well, you see, if everything in your platform is one single level memory storage thing, and you have an application in one part of your memory and the operating system code in another part of your memory, and that's part of how we separate things to keep things safe. Well, if you have a pointer in your application, now how do you manipulate that pointer? You add or subtract to it to get to other parts. For example, you're in a data structure. One point in the data structure is one pointer. You add some and get to another part, and that's part of the language. It makes perfect sense. Well, then what's to keep you from adding a whole bunch to it or subtracting a whole bunch from it and finding out, oh, where did I land? Maybe I landed in operating system code. Maybe I could change that operating system code. We couldn't let that happen. And so already with V1R2, we had to add this new thing called security level 50. We had to add initial hardware support to protect things so that the part of the operating system or the part of the single level store that had the operating system couldn't be reached into by manipulating pointers within an application piece of code. And so already this implementation we had of single level store had to have new architectural elements added to it to protect the platform. Another similar thing happened very early on in the AS400's architecture. You see, the System 38 had one very flat file system, but by the time we got to even announcing the System 38, there were lots of folks out there who are using hierarchical file systems. Now, we basically all use hierarchical file systems today. If you've got any sort of PC at all, or if you use any sort of Unix platform or Windows, you expect that you should be able to store a directory under another directory, under another directory, in subdirectories or folders, or however the terminology is. Well, System 36, as it turned out, actually had a file system that was already hierarchical, but System 38 did not. And so the AS400 had the System 36 and the System 38 file systems, but they didn't have a common one. The industry was starting to sort of get centered around a set of standards around file systems, which they called POSIX. And so AS400 had to adopt that approach and create something called the integrated file system, which could converge all of the different kinds of file systems on the platform in an architecture that was common across the industry, so that now as we began sharing files, people could share files within subdirectories and so on. And today's modern applications just assume that you're going to have a standard hierarchical file system. You can still write System 38 style file system based programs. You can do that if you want to, but you need to be aware that people in the outside world are assuming that there are going to be directories, subdirectories below that, and so on. And so we had to create a part of our architecture, the integrated part of our architecture, that would address that. And so we had to adapt to the fact that programming styles were going to assume a hierarchical file system, which is, of course, considerably more powerful than the flat file system that existed in the first place. Another key change happened early in the life, but wasn't adopted until a little bit later, was the recognition that programming styles were going to be changing as the capacity and speed of systems was going to increase. So when people back in the 70s and 80s wrote software, for those of you who haven't been around for a long time, you may never have experienced this, but back then it was important to keep your code as small as possible, even in its compiled state, because there just wasn't that much room on a system, and you didn't want to be paging things in all the time. And so people wrote software in very monolithic ways. One big piece of code, no subroutines, no callouts to other things. But over time, people started recognizing the value conceptually, intellectually, and with the capacity of the machine, the ability to actually do things in modules, right? Computer architecture made it possible for you to do things in modules, which were a lot easier to develop, keep intellectual control over, and then connect to one another so you could do reuse. In order for the AS400 to be able to adapt to that, we had to invent a new language environment, which was called the Integrated Language Environment, or ILE. When it first came out, people often talked about it as the new program model. Sometimes then the other stuff was called the old program model, or OPM. So if you hear those terms, that's where they came from. So we had to create architecturally this new environment for programs to be created in. And so this actually affected a couple parts of the architecture. Before you had ILE, you could only have resources owned by the program that allocated those or the job in which that program was running, and that's all. We had to create a third alternative that would allow you to have something get created in one place and used outside of that program, maybe in the same job, maybe not in the same job, maybe in this other group that would exist, so that you could share the resources you wanted to share and not share other things. And so we had to create this thing called the activation group, which combined several things together and allowed you to share resources where necessary across the things that were inside that activation group. If you've been with this platform for a very long time, you might remember when that came into existence. But the problem that I find when I talk architecture with so many long-time users of this platform is they tend to forget we had to add this to the architecture. We become so used to it that we feel like it was always there. It wasn't always there. It got added to the architecture in the days of the AS400, the earlier, but not right away, days of the AS400. And so there are many benefits from this. Now, as Tom mentioned, you're going to have access to all of these charts. I even have some hidden charts here that I can't go into. So if you feel like I'm moving too fast here and you didn't get every point, you're right. I can't spend time on every one of these charts doing every little one of these things. But when you get the PDF, you can dig in a little deeper to most of these topics. All right, so programs run within jobs. Jobs are implemented in this architecture by processes, which are lying beneath the MI layer. And those jobs and processes were a fine way of doing even virtualization, like subsystems and so on, as we started out with. And they were great until they weren't anymore. You see, comparatively, now we didn't have anything to compare it to originally, but when you start comparing it to how other operating systems were doing things, you could get a unit of work up and running on other platforms much, much, much faster with far fewer instructions being run to set something up. And so as modern applications got written where they wanted to kick off work asynchronously and do that very, very frequently, it was very difficult to do that on this platform because in comparison to other platforms, it took so much extra processing power to get a job with its associated process up and running and have the environment ready to handle new work that the application wanted to give it. In the industry, then, people created these very lightweight things called threads, which could be kicked off to a unit of work, be finished and be done. And people started writing applications for that. To implement that stuff inside of a job was very, very time consuming, and we slowed down a lot if that's how you wanted to do things. So we had to create a thread. So we created a thread. We created the architectural element of a thread, but when we did it as an operating system, the initial way to do it was we created one thread per job. Well, that just meant every time you wanted to create a brand new thread, you had to kick off a new job, which is what we were trying to avoid in the first place. But at least we got the architecture there for how we could create threads. Then ultimately, we, under the covers, changed it so that those threads didn't require a job for each of them. You could have multiple threads within a job. But if you tried to do all of these things at once, you got a mess of these threads across multiple jobs that were not in the same activation groups, and it got very messy. Well, we wanted a new application. This was our inciting incident. Lotus Notes was purchased by IBM. It was supposed to be, and it was at the time, a fantastic email and collaboration tool early on. And we knew that our system was being used extensively by businesses who are now adopting email. Again, many of you who are younger don't even remember days when email didn't exist, but email began to be something that every small, medium, large business needed to do. And so we wanted Lotus Notes to run on our platform so you didn't have to have a separate platform for this. Architecturally, that was not an issue in terms of running multiple things on the platform, but Lotus Notes needed threads. That's how it was built. And so we had to adopt the architecture that would allow multiple threads to run nicely next to each other, all set up from within the same job or related jobs. And so that required a significant new level of architecture to the platform. All right, another of the big things that happened over the lifespan of this architecture was that we got a chance to actually prove that one of the layered approaches to this platform was going to provide significant benefit. If you remember back to that very first picture that I showed you of the architecture of the AS400, there was this part of the operating system which was below that machine interface, this virtual machine interface. There were actually two layers of the operating system, a vertical microcode layer that sat on top of the horizontal microcode layer, and those things both virtualized the hardware. The idea behind this was that we could change the hardware and not have to change the programs that were compiled to that machine interface. Well, we really got a chance to prove that when we changed from the original AS400 hardware, which was a 48-bit processor. Nobody else had 48-bit processors. Okay, we had 48-bit processors, which was way more bits than they had. They were 8, 16, and 32. But we saw the future was going to be in 64-bit processors. So we needed to replace that 48-bit CISC processor with a new kind of processor. And already at that point, the IBM Corporation was saying, we're going to head towards a 64-bit processor that's going to be used by multiple platforms, the RS6000 and the AS400. So we're going to take the 64-bit RISC processor that we're inventing and make it possible for both AIX and AS400 eventually to run on top of those. In the case of IBM I, or AS400 at the time, OS400 at the time, this was, as I mentioned, the chance to prove that this technology-independent machine interface could protect our users as we change the 64-bit processor. But to do that, the vertical microcode and the horizontal microcode were absolutely tied to the original 48-bit CISC processor. So we had to write a brand new, huge layer of code underneath the MI and above this new RISC processor. Essentially, every piece of code that had ever been written below the MI had to be thrown out and re-implemented to do the same function and better on top of the 64-bit RISC processor. That was a huge change. Did the architecture change? Well, from your point of view, if you were a programmer above the MI writing RPG or COBOL or C and compiling your stuff, it really didn't change very much. As long as you kept observability, which was how we build those machine instructions kind of connected to the program objects, we could just do all the retranslation for you. But below the MI, it was a brand new story. We had set ourselves up to be able to move to multiple cores being used at one time, even though there weren't multiple cores at the time. We set ourselves up to be able to do that. We set ourselves up to be able to talk to disks differently. We set ourselves up to be able to talk to I/O differently. So all of that changed, all of that underlying architecture about how we deal with the hardware changed, even though it didn't seem to change to those folks who had followed the rules and written their programs and compiled them and kept observability over time. All right, so I am to my first little break, so I'm gonna let Tom talk for a minute and you'll see me take a drink or two.
Thank you, Steve. This has been really good to get updated on where we came from and where we're going here in the future. Just to remind you, while we're giving Steve a little break, Help Systems does do some thought leadership around the IBM I platform. We've been doing the IBM I marketplace study now for 6 years. We are planning again to do the survey in the fall. Look for that coming in the September timeframe. We also put out the annual State of IBM I Security Study. Definitely worth reading, definitely worth sharing with your audit team. Security has to be on your minds today during this epidemic, and why not educate your staff a little further? We do that, plus we have a bunch of free webinars around that topic. Then another thing that we do is a lot of one-on-ones with our customers and go through what we call a tech update or technology update, and where we kind of share stories and what's on your roadmap and what we're doing here at Help Systems. And the final topic is, if you haven't seen, we just did a webinar last week on the Solution Edition program for IBM I. Help Systems and all of our IBM I software is part of that program. That is also a program that's available for other independent software vendors or ISVs. As you purchase 924s or 914s, you can get a reduction in software, free services, lab vouchers, etc. So enough said on that, Steve. Let's move ahead to the next slide. And then at Help Systems, of course, we have a lot of software that runs on IBM I. We can help you out with backup and recovery and HA. We work on both Power HA, BRMS, Robot HA, Robot Save in that area. Document management, we help a lot of people. You know, obviously, with many of us working from home, you can't just depend on documents printing for you. You have to have this paperless today. Cybersecurity, we start out with our free cybersecurity scan. Monitoring systems, of course, we've been doing that for many years. BI and IBM I. If you are looking at new technology, we can do capacity plans for IBM I, really AIX and Linux on Power, and even competitive things. We can take a look at Linux on x86 and look at that workload and how it would run on the Power platform. And then, of course, automation. And then finally, while we're giving Steve a little break here, if you want to move to the next slide, we'll launch up our polling question. We do appreciate Steve working with us today. We also know that we can help you out there in many different ways, so feel free to select all that apply here. I'd like more information on capacity planning and monitoring. I'd like to talk about my BI data access needs. I need help with HA and DR concerns. I'd like help with document management and IBM I. And of course, the last one being is I'd like a free security scan. No matter what it is, feel free to reach out to us, give us an email, go out to our website. We'd love to help you out here. Speaking of that, we do have a couple of great webinars coming up. We have July 23rd, just next week. Ask the experts around performance on IBM I. Randy Watson's going to be joining me. He's awesome and has been helping customers with performance issues and sizing opportunities on this platform for as long as I've been around here. And then on August 5th, we're doing another free webinar on how to upgrade IBM I, and we'll be having an expert from the industry join us and share the topic of the steps you go through when you look at upgrading, IBM I 7.1, 7.2, 7.3 to 7.4. 7.4 already has been out there for a whole year now. So enough on that. I'll close out the polling question, and I thank you for responding, and we'll share quickly and then move it back to you, Steve. I hope you had a great break. I think we timed it perfectly, about 9:35. I promised you we'd give you a break.
All right, it worked out great. Thank you very much. All right, so let's move on. All right, we've evolved this architecture now to a point that would have been like pre-internet. Now I'm going to slow down on some of these things now because there are points to be made about how the modern era has affected the architecture of this platform. And the modern era essentially starts with when the internet came, when web pages came. This, by the way, is the very first web page that was ever created. It's now virtually in a museum somewhere. This whole hypertext protocol, hypertext transfer protocol, HTTP, came into existence, and people wanted to interact with the systems that they were on differently than ever before. It was going to be more than just what was green screen, but every system had its version of a text-based thing. Now we wanted to be able to have text that could go other places, eventually could have pictures and so on. All of that required a thing called a web server, and we understood that within the platform. And so we pulled into the operating system the first web servers. Now, the first web server we pulled in was the first web server that was created by research, the CERN-based web server. You could only have one instance of it. Then in V4R1, we allowed you to have multiples. But that web server was a research-based web server, and they, at the time, did not want to get into the business of keeping that thing up to date. They were educators, they were researchers, they were not product people. But the open source world was beginning. People were recognizing the inherent value of having a web server that could serve up things like HTTP and the following protocols that happened after that. And so open source started happening. And so we committed as a platform that we were going to have an open source version of a web server. We weren't going to write our own. We weren't going to take something that was within the software group within IBM at the time. We were going to commit to doing the open source version so that our users would have the same thing that was being used in the outside world. And so we created an Apache-based web server. Now, fortunately, we had already done the initial work on multi-threading, which was incredibly important because you couldn't do web serving without the ability to kick off threads. That's how web serving is done. A piece of work comes into that server, and you create a thread to be able to handle that. But there were some things that didn't really exist at the time that web serving started that needed to be built into the platform. You had to have digital certificates because that's how you did two key things. Number one, proved to the platform who you were so we could tie your identity in some other place to the identity that you had as a user on the platform, or not if you didn't have a user ID on the platform but still wanted to get some information from it. And digital certificates were used to encrypt the traffic between one machine and another machine. And that happened all the time. People had that requirement immediately once they started doing web serving. We therefore had to create a brand new architecture within the platform using jobs, processes, threads, and tasks, the underlying ways of doing unit of work. We had to figure out, okay, this web server thing is not going to be the only kind of server we're going to have. Already in the marketplace, there were these things like database servers and other kinds of servers, and they were being built up out of these thread groupings in our platform, a job with a bunch of threads and so on. So we had to create a new architecture. And all of these new web serving based applications, these new workloads, were taking up storage, but only for a brief period of time and then letting it go. And so this thing called Teraspace had to be invented as part of our platform. So again, in the early days of AS400, we never had a need for this, and so we didn't have an architecture to built around it. And it was actually quite close to the time that the AS400 name got dropped that many of these architectural elements began to appear within the operating system. So digital certificates, tying to servers to prove who you were and make sure that you were encrypting traffic, handling storage differently than ever before. All of that came into existence in the later stages of what we knew as OS 400. Now, to this point, we haven't really talked about how the database is involved, and I would be remiss if I didn't talk about it. So I'm going to talk about the database for a little bit, and then at the very end of that, we'll kind of tie some of these things together. You see, the database from the very beginning came in with what was called the classic query engine. If you want to get an answer from a database, and that's really what a database is, it's a place to store data so that you can get a business answer. I want to know some information about the accounts that I have, or I want to know how many orders I've received, or whatever. You're asking a question of your data. Well, that initial engine that we had architecturally was very, very simple. You would ask it a question in form of a query, and it would give you an answer, but that's all it could do. DB2, from the time the first AS400 came out, started implementing SQL because there was a promise in SQL that eventually you could take advantage of knowing that you were dealing with SQL and do some special things to the database that would improve its responsiveness over time. Using SQL, if you knew you were using SQL from the beginning, you could learn from the past. So as you did future queries, you would take advantage of the fact that you had done other queries and you would have built your data infrastructure so that you could respond more quickly, combine more information, and get better throughput with your queries. And you could then learn from prior queries and get lots and lots of new queries that you never thought of that gained a benefit from the fact that you had done the prior queries. But to do that, you had to use SQL. You couldn't be using the old style of queries that existed in System 38 or System 36. Okay, so we had to create a brand new query engine that had a lot more to it. It was a lot more complicated, but it kept track of things. It kept track of how was data accessed by this query and by these many, many, many other queries, and how could we reorganize things in the underlying indexes and so on, so that as the most common queries happened on this machine, we were able to respond more quickly. Again, this makes us very, very, very different from other platforms where the database is separate from the operating system. In those environments, you have to have database administrators who look at statistics and notice that various queries are happening, which are resulting in many specific tables being used in specific ways so that they use their database administration interfaces to modify how the data is stored. Well, you don't do that on IBM I's DB2 because the database is part of the operating system. It knows how the file, which is really an index, is being used to implement it, and it can change those things dynamically under the covers. So your machine will run best for you. It'll run similarly to how another machine is running the same workload somewhere else, but it's going to run better for you because the way you use it than their system would. Okay, so each system ends up being sort of unique, and that's the power of this SQL query engine. The thing is that this query engine was completely different from that original query engine. So as we introduced it, we needed to avoid disruption. We needed to have people be able to ask their questions of their database and get an answer. But over time, if those questions came in as SQL queries, we could learn more and more and more from them. So while originally almost all the queries, when the new query engine came out, all the queries were handled by the old query engine, over time, the new query engine could learn more and more and take over more and more. And that's what's happened. Still today, there are some queries which are still handled better by that old query engine, but almost all of the queries, all the SQL queries, are handled by the new query engine over time. And architecturally, we protected you from that. A few of you who've been around for a long time probably remember specific cases where you had to report an error, and hopefully we fixed that to your satisfaction, because as we change to this very complex thing, there are always errors that creep in. But architecturally, the architecture of this was to be able to move smoothly through it, and for most of our clients, that certainly happened. Now, one of the key things about databases over time was that people began to expect that this original style of database, which was stored in rows, was optimized for rows. What's a row? For example, your customer name, address, what they purchased from you, all that stuff is one thing, okay? That's a row. Well, people started doing analytics on their data, and they found that many times they didn't need to know anything about that particular row. What they needed to see was trends. So any given customer wasn't important, but what were the products they were buying and at what time of day and through what resources? Well, as they began to want to do analytics on the data, do more than just run a business, but look at how that data was coming into existence and being used, there was another way of organizing a database that came into existence, and that was column-based. They would store the data such that the items being ordered, for example, were easier to find. They were all grouped together. So rather than storing things in a row base, they would store things in columns and connect them to the data. For example, this user did, yes, in fact, buy this thing, but that's not the important thing to me right now. What's important to me is that all these things are gathered in one place. Well, that's fine. What other databases did was to reorganize their database into column-based storage. But that slows down your traditional workloads. It makes it harder to do standard reports like month-end reports for individual clients and so on and so forth. Okay, well, our DB2 did things differently. We invented and patented a thing called encoded vector indices. The encoded vector index, which allowed us to continue to store things in the most efficient OLTP or row-based way, okay, but also built along with that some metadata that would look like it was in columnar format. So if you wanted to do analytics, we would recognize you were doing an analytics kind of query, and we could point you at a different view of the data that internally looked a lot more columnar. And this incredibly improved the performance of many of the things that were going on. This just happens to be from the time that we did the EBI stuff. This particular benchmark improved by more than 20% because all of a sudden they were able to look at the data in a columnar way, do an analytics-based thing across data that they had been using in a solely row-based OLTP way before. I'm sorry if you don't recognize some of these terms. Again, some of that data is there, but the point is we didn't have to change how we did things. We didn't have to disrupt the kind of performance you were getting from your normal workloads to add the ability to do these new modern workloads. And that required an architectural change with how the data was put together under the covers, but not in a way that required you to do anything different with your database management. Another thing that happened just at about the time, not quite at the time that OS 400 was going to go away and become i5OS, was this thing called independent ASPs. Of course, every business had to have some sort of plan for what happens if my system becomes unavailable. But of course, for years and years and years, the answer to that question for many of our clients were, well, we did tape backups, and if we had to bring a new system in or we had to go to a different site because my site got hit by fire or something, we would just restore from tape and the business would be back up and running. And that was a fine answer for many years, but many, many businesses began to get to the point where they needed to be able to switch quickly. And so what they wanted to be able to do was to take their core key data, have it be on storage that they could quickly attach to another system. Well, that doesn't work very well with single level store. With single level store, your system owns a certain amount of storage. It has all of its addresses, and those addresses are unique within that system. Those addresses do not match, cannot be moved over to another system. That doesn't work. So we had to take this idea of auxiliary storage pools and create an idea called independent auxiliary storage pools. Independent in the sense that it didn't matter that this storage pool with its set of single level store addresses was taken from one system and put on another system. That architecture was never envisioned when we first created auxiliary storage pools or when we first created single level store in the first place. And so in order to allow a piece of single level store to migrate from one system to another, we had to create a new part of the architecture. In fact, the Power H8 product that Tom mentioned was built on this whole idea. Another key thing happened in the storage space, and I mentioned it briefly when I talked about web serving programs. The style of writing programs, once threads became the natural way to write units of work, was for a thread to have a certain amount of storage that it used for only the lifetime of the thread. A thread doesn't, generally speaking, live for very long. It comes into existence when a request comes into the system, and then it does its work and it goes away. So that thread may never actually store anything on storage. It might write some record to a file, or it might show something out to a user and that looks like it's writing something to a file. But in general, the work that it's doing, the processing that it's doing, is never going to show up on storage anywhere. So it does not need to be backed up by physical storage. So in essence, all of the work that's being done in a thread needs just temporary storage, something for me to work in, a piece of scratch paper for me to work on while I'm doing my work, and then it goes away. Well, when we first implemented threads on the platform, of course, all the storage that we had was single level storage. That meant that even though your storage was temporary storage in your program, we had it backed up by physical storage somewhere. And so that could get paged out, which meant it had to get paged back in again if it had gotten paged out, and that could slow things down. What we needed to invent was a truly, totally temporary set of storage. And that's what Teraspace was created. Now, Teraspace is more than just temporary storage. It's also a very, very, very large address space, because you see, these threads were being created assuming that they had all the temporary storage in the world. They could be on the system assuming that they didn't have to worry about resources from any other place, so they just had their own temporary storage. So we had to create this new architecture that sat alongside single level store, so that if you had a pointer in Teraspace, you had loads of storage. It was never going to be written out to actual physical storage, but you didn't have to worry about running out of it. And we had to create these lightweight pointers that could be used by the programs running in the thread, that could be used very, very, very quickly, but again, never stored. So Teraspace was added. again, late in the evolution of OS 400 as we began to approach i5 OS, so we could have a new way of managing the storage. So now we've reached about the point where we finally did our last name change. Just so you're aware, it was 12 years we lived as AS400. We became Power Systems and IBM I 12 years ago with 6.1. So now, as of 2 days ago, we're actually longer lived as IBM I than we were ever as AS400. But there were some architectural changes that happened when we became IBM I 6.1 on Power Systems. And now we're getting into the most modern stuff that happened within the architecture. One of the key things was that when we changed to 6.1, we actually changed the underlying processor architecture again to improve your security and integrity, to improve your performance, to remove a bunch of limits. And so to do that, we had to do another retranslation. Now, we didn't change the size of the processor or so on, but we changed the capabilities. And one of the key things we did there was to make it impossible for you to use a pointer to move within the stack of your program. I already talked about way back at the beginning, you couldn't move from one place in your program, your address space, out to the system's address space. But still unprotected was the program stack. If you are a programmer or if you studied programming, one thing you'll realize is that as a program is running within a processor, it has this thing called the stack. It's all of the data that's needed by the program very quickly. And as you call programs and programs, you put more and more things on the stack so you can quickly get back to them. Well, before 6.1, the machine had a single stack. So if you had a pointer to something in your program and you could infer from its operation that it was probably in the stack, you could modify that pointer and get down into system space on the stack. This was a bad thing, and there were people doing bad things with it. There were, believe me, there were. So we had to create an architecture on the processor which would allow us to have stacks that were split. So we could have user programs have pointers that were only accessing their stack, and they could never do anything to get to the stacks that were running on the power processors that 6.1 was on top of. Okay, so again, this was something that you didn't have to notice, but you could notice if you wanted to, just by the nature of the changes that we put in place. Okay, so that was key. We also, I mentioned Teraspace before. We had implemented this virtual temporary storage called Teraspace only in software before. And so we could not speed that up because it was only in the operating system that it happened. But by the time this release happened, 6.1 happened, we had built into the hardware that 6.1 was going to run on top of the ability to handle Teraspace pointers. They were similar to, but not the same as, the kind of pointers being run on AIX, but they were similar, and so we could build into the processors how to handle them. And so now we could implement all of the Teraspace support using the hardware, and we didn't have to rely solely on sort of simulated software within the operating system, which improved both your integrity and your performance. And the PowerHA product, which didn't exist before 6.1, came into existence and got built upon those independent ASPs that we had architecturally added to the platform a little bit before. And that created the ability to have these things called administration domains that we can administer a cluster of things around and so on. So all that was part of this 6.1 change. So when we became IBM I back in 6.1, we actually did a number of things that were architecturally unique to now IBM I that didn't exist before in OS 400 or in the briefly named i5 OS. Okay, that allows me to bring in my first customer story. You see, there were clients, there exist clients, many clients out there who need their businesses to be up and running basically all the time. And so there are many client stories that take advantage of this independent ASP capability and the associated use of storage area networks, which I didn't have time to get into, but is underlying all of this. We no longer had to have all of our storage be managed specifically by IBM as direct attached storage. It could be storage area network storage. And so China Merchants Bank is one of our leading customers who uses this technology. They can swap from their primary system to their backup system in under a minute by using the capabilities of independent ASPs, the PowerHA product, and the storage area networks they can attach using this new architecture. Would have never been possible without those architectural changes, period. Could not have done that with the original existing architecture until we got to that point. Another key enhancement was to the architecture was the creation of PASE. Now, by the time we reached the year 2000, AIX and then OS 400 were able to run on the same power processors. So we were able to create within IBM an environment where we could actually have the AIX kernel running in the IBM or OS 400 instance inside our partition, our virtual machine. So we created this thing called PASE. It's Portable Application Solution Environment, but really what it is an AIX runtime. PASE gets memory to run things in PASE from the same pool of memory that Teraspace uses for the AS400's native ILE environment. So anytime you're running in PASE, you're using the same kind of storage that you would have been using if you were in ILE and using Teraspace. So all of that exists, and it has enabled an amazing transformation of this platform from being something where you had to know the AS400's architecture to now being able to do things that are in the open environment. Pictorially, the architecture is that you've got the operating system, and next to that you have shared libraries, and we ship it all together. And when you want to run in the PASE environment, you're running in a binary that was compiled for AIX. Now that binary, that AIX binary, assumes some abilities to get from the kernel resources like memory, for example, or access to I/O. To actually make those things happen, since you're not running in AIX, you're actually running in IBM. We had to create these sort of connector things called syscalls that will send the request to our lowest level of the operating system called SLIC, and it makes sure that the PASE programs get what they need. All of that then allows you to run on the power virtualization hardware. So now today, we have the ability to run the existing long-time traditional languages like RPG and COBOL, C, C++, Java, which is becoming as traditional as anything, okay? But we also have the ability to run many, many, many open source languages, frameworks, and tools, because we have now, as part of the architecture, this essentially open source runtime environment, which is implemented by PASE as an AIX binary. And that has allowed many of our clients to extend beyond what they could do with their original programming staff and their original programs. You see, you can write RPG, modern RPG, to do things like web pages and mobile devices, but there are huge libraries of things out there in the open source and languages that are far more tailored to being able to do that kind of thing. So we have clients like RPC Superfos in Denmark, which has their back end still written in the traditional RPG that connects very well to DB2, but as they wanted to modernize and incorporate new technology to do web services, to do mobile devices, to do things that were commonly used by the programmers that they have all around the world. They grew outside of Denmark to being an international company. Python, Node, those things are known by programmers everywhere, and they're easy to do modern interfaces with. They connect that to modern RPG because modern RPG can call out to other programs, be called by other programs, use web services, and so on. This is one of many, many, many client stories we have where, because we have this architecture that is an open source runtime environment in PASE, they can modernize their applications to do anything. Again, without that architectural change, it wouldn't have happened. Hatco Corporation, similar kind of thing. They're a manufacturer who has wanted to modernize what they do so that they can interact better with their suppliers and their customers. And so again, their backend still exists, but they use PHP and Node.js. They use tools from the open source community, Git and so on, to be able to do their software development now, both in RPG and in open source languages. If you follow me on Twitter, you've probably seen the link to many, many of these customer stories. Pretty easy to find by going to the IBMI homepage. Architecturally, what this means is that now we have these additions to the architecture. And so while this never existed in the original architecture, it is part of how we do the integration cornerstone item now. We can now integrate technology that we never had before because we have PASE. And those PASE applications have the ability to run next to native AIX binaries. They are native AIX binaries, next to the runtime that talks down to the slick internal code. And all of that uses the Power hardware underneath it, because you can run your Power processor in tags active mode, in other words, in the single level store mode that's used by MI programs that were compiled using single level store. Or the Power processor can be run in non-tags active mode, which is the way AIX does things, which is the way we do Teraspace pointers. Okay, so there is a little piece of the Power hardware which is tailored to which way do you want to run, how do you want to treat these addresses. And all of that is virtualized through this thing called Power VM, which is the hypervisor that exists, and that leads us to cloud technology. Since about the 7.1 timeframe now, we've had the ability to create partitions of IBMI and AIX and Linux on Power on top of the Power hardware and manage those things as if they are in their own machine by themselves, or as if they're in a machine sharing other things. Now, that virtual machine, that ability to do LPARs, actually existed on late AS400. And that virtualization machine that we created, the hypervisor we created for AS400, became Power VM. So our hypervisor technology from AS400 became the hypervisor technology that was used by all of the operating systems that run on Power hardware. It was as of 7.1 that you could start doing things that were really cloud-like. So while you could do resource sharing on 6.1 and 7.1 and virtualizing your I/O in 6.1 and 7.1, well, that went back to 6.1 and the capabilities that we had in the initial IBMI release. It didn't exist before that and was added to when we started doing the cloud technologies like network install, the ability to install from storage that was network connected instead of from, say, tape or disk. Okay, you could suspend your environment. You could deploy an image of IBMI that had been saved off somewhere. You could move a partition that was running from one physical system to another using IBMI and the virtualization layers below that, Power VM, which, as I said, was the original AS400 hypervisor, now implemented so that AIX, IBMI, and Linux on Power could use all of that. Okay, so as of the 7.1 release, we began to get the underlying technologies that would allow us to be a cloud-based operating system. Again, never possible with the prior instantiations of this architecture, now completely possible. The things that we rolled out during the 7.1 timeframe using technology refreshes, which is another addition to the operating system architecture, but I don't have time to deal with it right now. Okay, by adding technology refreshes, we got you to the point where you could use IBMI in a cloud type environment. Now, whether public cloud providers did it or not, that was essentially unimportant at the point. The point was we needed to get IBMI to that capability. And our business partners and our ISVs began to use us. We've got client stories like the solution vendor King3 Systems, King3 Solutions, which had prior to this sold their software by helping us sell machines to their clients, but now began to run their system themselves and use their software as a service cloud capabilities that were on IBM I and Power Systems to be able to do a software as a service offering for many of their clients, and then grow their client base because now clients didn't have to manage their systems anymore. Okay, same thing happened with Svenska Handelsbanken. In the late 90s and early 2000s, they became a major player in Scandinavia and Northern Europe in the banking industry. Banks would have their own I-series box with their Svenska Handelsbanken software on top of it. Over time, Svenska Handelsbanken brought all of that workload to their own internal cloud. And now they don't sell systems anymore. They buy systems from IBM and they grow their client base by having a software as a service banking. In fact, one of the big cloud providers of IBM I existed before any public cloud provider was out there, Connectria built and still builds clouds. Many of our partners builds clouds of IBM I on top of Power. And today you can go out to the IBM cloud and get yourself a Power Systems virtual server, and IBM I will run on top of it. And all of that is made possible by the architectural changes that we put in place starting in the IBM I timeframe of 7.1. So again, not back in the AS400, not even in the I-series time, but back then. This, by the way, has allowed us to adopt the cloud management capabilities that are out there in the open world. One of those tool sets is called Ansible, and it allows you to manage your IBM I instance the way you manage other cloud instances. We just have these specialized IBM I modules that plug into them. It also allows you to deploy your software in a continuous integration, continuous deployment way, because the Ansible tools are used for that as well. So you can get into a CI/CD or DevOps approach using tools today because we have these underlying cloud technologies. Now, one of the most recent things that we've added to the architecture helped us address this critical business need for continuous availability. There is a difference between high availability and disaster recovery and continuous availability. In high availability, you have some willingness by the business to have your workload suspended for a brief period of time while you switch from one system to another. In disaster recovery, one of your locations may suffer a disaster and you need to be able to bring your system up and running, your business up and running in some other location. Those are valid things and everybody still needs to be able to do those, but continuous availability is I have to have my data center serving my clients with my workloads all the time. And to do that, we created this product called DB2 Mirror, which came out in conjunction with the 7.4 release and required an architectural change, which was quite dramatic within the operating system itself. Now, when people do continuous availability, what they say is they want an active environment. They want to have in the same data center 2 systems and have both systems be able to actively access the same data at the same time, so that if one of the systems has to go away, they can continue running their business on the other system at the same time. DB2 Mirror is our product that allows you to pair 2 systems together and lock the appropriate objects as they are being used, so that both systems can appear to be using them at the same time, even though at any given time only one of them is making a change. So this DB2 Mirror product came out to allow clients to do that. And one of the big benefits you're going to get from that, by the way, is the ability to do a rolling upgrade. You could pair these 2 systems together, have workloads running on both of them at the same time, sharing the database at the same time, and you could bring one of those systems down, all the workload is going on the other system, change it, for example, add a new operating system release, bring it back up again, resynchronize, the workload continues to run while that resynchronization happens, and now you have 2 separate systems running the same data, but with different versions of the operating system at the same time. That is something that DB2 Mirror is going to provide. And in order to do that, we had to create a new architecture under the covers, which would allow us to do this thing called RDMA, Remote Direct Memory Access, that would allow us to essentially share pieces of memory across two systems using this technology called Rocky. And then we had to create a new architectural element within the operating system, which we call the engine, which notices when a replicated object is being changed in a way that has to be sent through that RDMA process to be updated at the very same time with this direct memory access on both systems at the same time. So both engines have to be in sync, talking to one another to change those things. So we typically show how this works by showing you that when, for example, a database record gets added on one system, it uses this RDMA technology to make sure it happens on the same system or on both systems at the same time. And that's great, that's wonderful. It's not just database though. I want you to understand that it's not just database. We have lots of different object types that can be done, and you determine there are rules that this engine follows for how it does things based on how the user has configured it. And again, we had to create an architecture for how those rules would be implemented. I apologize for going so fast through this. You can tell there's a whole lot to this, and we are reaching the end of my time. So I just want you to know one more thing. In addition to all of that, all of the stuff we've done for continuous availability, all the stuff we've done for cloud, the new way of accessing resources for an application is very cloud-based, and that is also being used to make cognitive or artificial intelligence, machine learning workloads available out there in the world today. And so there are clients of ours who are using the new architecture of this platform to be able to consume web services and export web services to do things like H2O on IBM I, next to IBM I, out there in the cloud, connected IBM I via services. All that is possible because while we do have this core architecture, which is still there from the days of the AS400, we have had to add so much around it to make that happen. So now you can have your native solutions, which were the only things you could do back in the beginning, and only on a couple of these languages. Now you can add that to open source, you can connect it to Linux, you can connect it to the cloud. All of this is possible because of the architecture changes that have happened. What has been so remarkable about this operating system is that we've known since the very beginning technology was going to change. This operating system has had an architecture that we've been able to evolve to change with it so that we don't have disruption for you. And we continue to use every bit of our brain power to make sure that as we evolve this architecture into the future, you will be able to take advantage of the brand new things that are available. So that no matter what your business needs to have done, the architecture for IBM I can do it. That's the end of the presentation. I think we're at a Q&A time, but I'm sorry, Tom, I ran over by a couple minutes, so I'm just not sure where we are.
Well, I love your passion for the topic, Steve. I mean, there's no doubt we've gotten fantastic responses from what you were sharing today and the evolution to IBM I where we sit today. And the fact that it's been IBM I now longer than AS400 is really a nice tidbit for the audience to take away today for sure. Thank you. You can pop ahead one more slide. I just thought I'd throw up some of our product solutions that we have. Oh, right there. That's perfect. And we thank you. Again, we do a lot on IBM I, and of course, we can even do pen testing of entire organizations and many other things across the board that helps systems. We had a few great questions. We did record today's event. It will be emailed out to you, and there will be a PDF of Steve's handouts, along with I sent a note in the chat for the upgrade webinar. We got quite a few questions on that also. One question Rafiq has is, what functions still use CQE engine?
Okay, so there are still clients who have old queries built to the old interfaces from System 38 and System 36. They do. And then there are a few very simple queries that run that are just faster, but it's very, very few.
Yeah, I would say if somebody's still using Open Query command or interface, they're probably still using CQE, right?
Yeah, probably. Yeah,
So get rid of that. You don't need to do that anymore. Kind
that's
of
right.
a similar, that's probably the easiest way, right? To handle that one. A similar question where is this one now? I got so many here just at the end.
That's okay. And
All
we'll
right,
try
I
to answer
guess,
them offline if we have to.
I think it was, how can I eliminate access paths occurring? Is there something other than logical files I can use so I don't have access path issues on Power 9?
Yeah, it doesn't matter that it's Power 9. The answer to that is there are techniques, but we're not going to answer that question here. What we should do is take that, get Scott Forsty to respond with pointers to some best practices things, because I understand what this guy's asking, but we just don't have time to ask questions back and forth to see which direction you got to go. Okay.
Well, yeah, what's the best way, right? And
Yeah,
that's the biggest
yeah,
problem with IBMI, right? There's more than one way to do things,
definitely.
especially when you pile in open source type technology too.
Yeah,
Um, People love your dragons in the background.
thank you.
They're they work for a warehousing management software company that runs on IBMI. How can they get more recognition out into the IBMI space and obtain new customers? What would you recommend?
Well, boy, there are a lot of things to answer here.
So this is an
Number one,
ISV, right?
yeah, number one, if you're an ISV, please be paying attention to my blog, because this year we are reconnecting with our ISVs and giving you a lot more resources than we have in the past few years, including doing special connections with our ISVs to identify the paths where, if you haven't done modernization, can really show your clients additional value that you can get quickly by incorporating some open technology. And then probably you're looking at how to do a cloud or software as a service environment. Many other ISVs are finding that they're competing very well in their industries if they have their own software as a service that has been made enabled for mobile devices and so on. I'm not sure whether you've already done that or not. So anyway, connect with us. We'll see where you are on your modernization roadmap, and then we have next steps we can help you with. Usually it involves incorporating open technology with the back-end stuff that runs so very well in your SQL or your RPG database stuff.
We have so many questions now, Steve. I'm going. Some of them are like that index question, so I'm going to save all those chats. We'll get them back to you. As I told you, I'm actually going to be taking off on a little bit of a
Yeah.
side trip and do some kayaking and stuff. So might be Tuesday or so before we get back. Some of these things depend upon our marketing team. Somebody asked about performance issues. What do you do? Well, you can certainly connect with IBM at Help Systems. We also do some performance services around any kind of performance issue on IBM. We can at least tell you where your problem is and help you out. And IBM can do that too, either through lab services or getting started with, I guess, level 2 support, probably, I would guess, on performance issues.
Yeah, if it's something where something slowed down all of a sudden, it's probably a service thing. If it's been over time, things have been getting slower and slower, it probably is something you can modernize. And as Tom said, I mean, they have tools that they sell. We have some sort of rudimentary things that can show you what's going on, but then how to get yourself out of that is often use the advice of experts, like the experts that Tom has.
Yeah. You know, and I'm going to leave the group with one more opinion of mine, Steve. And we've had a couple questions kind of around this topic, and it's, how do I get involved more in the IBMI community? And honestly, I think there's a couple of great ways to do that. You need to be a little more social. You need to start sharing what you're doing on the platform. We had somebody say, I'm an ISV, another person say, I'm an independent consultant. What can I do to get more recognition that I'm doing things on IBMI? It's LinkedIn. Connect up with Steve, connect up with myself. We'll get you involved that way. It's Twitter. Steve does a great blog. There's other people that, like Scott Fortsey, that does some great blogs and stuff like that. Get involved socially, because it's a unique world today in marketing, right?
Yeah. Yes, absolutely. And those two things that Tom mentioned, I'm going to just repeat them because they're so important. LinkedIn has a number of different groups related to our technology that share what's going on right now, and questions get answered and so on. And of course, LinkedIn is one way that I share when new things happen. But Twitter is, I'm sorry if some of you have some bad impressions of Twitter because of how it's used for various things, but But if you just want to use it for keeping up to date with technology and getting in touch with other people, it is a very good way for that. If you follow the hashtag IBMI, #IBMI, you will see all sorts of things that are going on in the IBMI community. And if you want to make people aware of what you're doing, you use that hashtag, write something on a blog somewhere, or create an article or create a paper, and people will see it. There's a large community of folks. In fact, that's where most of our open source community does their work, under the hashtag IBMI OSS, open source software, IBMI open source software. They stay in touch with one another that way, and then they have their own special places they go off and do their technical talking, but they connect with one another using social.
Well, Steve, not to steal your line, but I thank you for joining us today, and I thank you to the customers that joined us. And I guess try to enjoy your summer. Unless you're listening to us down under, then enjoy your winter and have a wonderful day.
Yeah. All right. Thanks, Tom. Great.
You're welcome. Bye-bye.